doing your work, it is very important to complete the homework, okay? Just like Iman is doing, Iman, so you guys should do it as well. So today we are starting with sound. Sound is a relatively easier chapter, and hopefully we'll just finish in today's class. So when you're looking at sound, we should basically remember that sound is a longitudinal wave, okay? Sound is a longitudinal wave, and it's formed in a medium which vibrates parallel to energy transfer, okay? Now when you make these waves, you guys should understand that there will be parts of the wave which are closer to each other, and there will be parts of the wave which are far away from each other, okay? Like this. So these parts which are closer to each other, they are called compression, and the parts which are like away from each other are called rarefaction, okay? So now we'll just write compression with a C, rarefaction with the R. This is a compression, this is a rarefaction, this is a compression, like that. So basically when the sound is generated, it also shows sort of, it's because of the pressure difference that is created within air or any medium. So we can basically display it using a pressure wave as well. Like, what you guys should remember is that if you have pressure on this side in pascals and you have time or length, whatever you're looking at, so where the compressions are here and where the rarefactions are, then we're going to look at the compressions, we're going to look at the rarefaction, we're going to look at the compressions. So compressions are the point which wave basically pushes itself into, so it means it will have the highest pressure. At rarefactions you have the lowest pressure because the particles are really moving away, and then at compression again it will have highest pressure, and at rarefaction again it will have lowest pressure and highest pressure, and the and highest pressure, like this. So just remember that at compression pressure is highest, and at rarefaction, in fact, the pressure is negative. Pressure is lowest and it's negative as well. Negative pressure means that it's basically less than the atmospheric pressure that's there, okay?
So the x-axis is the wavelength, right?
Yeah, it could be length, it could be time, anything you want to display it on. So it's not important. The important part is the pressure that you should understand, okay? Is it clear?
Yes, sir.
Iman, how are you? Hussein, Shaviz, Caroline, Yusra, and Ismail. Okay. So then we need to know the speed of sound, and you need to remember this. This is very important because they keep on asking this. So speed of sound in steel is about 5,000 to 6,000 meters per second. So it's fastest there. Speed of water, sound in water is around 1500 meters per second. And air, it is like 300 to 350 meters per second. So it could vary in air. Now, but what you guys need to remember is that sound cannot travel in vacuum, and to prove that, we also have an experiment that is called bell jar experiment. Okay, in the bell jar experiment, we have a bell in a jar, obviously, and then a vacuum pump. Yes, air pump basically.
Okay, just stop just for a second, please. Thank you.
Yes, we're right now.
Yes, sir, thank you, ma'am.
Okay.
Sir, do we have to memorize the speeds?
Yes, it's very, very important to memorize the speeds. Okay. Now, to prove that sound doesn't work in, like, it doesn't transfer energy in vacuum, it needs a medium. We have this experiment. So it's very simple. So we can write that when air is inside the jar, we can hear the sound of ringing bell. When air is pumped out of the jar, we cannot hear any sound of ringing bell. Is it clear? So basically it means that sound cannot travel in vacuum. So if they ask you this experiment, you just draw this diagram, write these 3 points. Usually he'll ask you this for 4 marks. On recent papers he has never asked it, but you never know. Okay, write this down please. Okay, should I go forward now, everyone?
Yes. Yes, sir.
Okay, cool. So then we are gonna go towards the next part. And it says sound wave is traveling through water. What is the possible speed of the wave? Who can tell me this? Anyone?
See.
Yay! Now you guys understand why it is very important to learn those, okay? Now, the diagram shows examples of wave motion. Which waves are longitudinal? Yes. What do you guys say?
4.
And there's one more.
D.
4 and 2. That's right. This is also longitudinal because it's creating waves in air, right? Like this. Okay, very good. And then we're gonna go forward. Then it says the speed of sound is different in different states of matter. The speed of sound in liquid water is this. Which correctly labels this? Yes. Who can tell me this, please?
C.
So in ice, it should be more than this, and in less than this. Very good. Very good. You guys now understand that. Okay. So then this question is very important, where it says how the cone of the loudspeaker produces this sound. Okay. So it says 15,000 hertz sound should be created. So we're gonna say number 1, the as the as as the current is switched on, okay, the cone of the speaker moves to and fro. To and fro means backward and forward, okay. 15,000 times in 15,000 times in 1 second. This causes energy transfer parallel to oscillation, that is when longitudinal wave is created. Longitudinal wave is created. Is it clear, everyone? That's what you got to write. Then it says the speed of sound is 330. Calculate the wavelength of sound. They have given us the frequency. So in sound we also use the same formula, V is equal to F lambda. So 330, frequency was 15,000 and lambda. Who can tell me what the answer might be?
A 0.022.
0.022 meters. So write the units. Units are very, very important, please. Then we are gonna go to this one. I think this one you should be able to do yourself, because this is very easy. You just need to write the definitions, and then we're gonna go forward. Okay, so so the next thing we're going to do is we need to find the speed of sound in air using light. Now how do we do this? So the experiment is when two people, one with a flare gun, one with the stopwatch, are standing a long predetermined distance apart. So when the first person shoots the gun, the light travels immediately to the other person. So as the person sees, he can turn on the stopwatch. But the sound takes a while to reach. Like sound takes a bit of time because sound is much slower than light, right? So when the sound reaches, he can stop the stopwatch. Okay, so we're gonna say number one, when person one shoots the flare gun standing a predetermined distance apart, then the person 2 starts the stopwatch by looking at the flash. Okay, because light travels really fast. Then he stops the stopwatch when sound of the gun reaches him. These experiments are also used in like paper 6, so you should really pay attention to them. Then using speed equals to distance, that is d, divided by time that was taken on stopwatch, we can calculate speed of sound. the experiment is repeated multiple times and average of time is taken to reduce human reaction error, because the person may start a stopwatch a bit late, right, or soon, so we need to ensure that's accurate. Okay, let me know if you have a question here. Okay, should we go forward now? Okay, so the next experiment is about using echo. This is a very important one, and the questions will be there a lot of times. So echo is basically the reflection of sound. So what happens is one person claps, so the wave sound is generated. Sound goes like this, and when it hits a plane wall, it is reflected back like this. So it travels a distance d and then comes back with the same distance, and the person standing next to that person can just stop and start the stopwatch. So what you're going to do is standing in front of a plane wall, first person claps. Okay, second person starts the stopwatch. The moment the first echo is heard, he stops the stopwatch. Then you can using speed equals to 2 times the distance. Now please understand that, very important point, because it goes and comes back, so you use 2 times the distance. And I'm just writing this in case of echo. You should always do that, whether it's in in water or air, whatever. We can determine the speed of sound. Okay, then again, because it is done by humans themselves, so repeat multiple times and take average of time, okay, to ensure a much accurate value. Alright, anybody who did not understand this, please let me know. Anyone who thinks my stickman figures are really good, they can also say, sir, you're too good. Nobody thinks like that? That's so sad. Alright, Zainab, Iman, Imal, Smiley, Yusra, Caroline, Chavez, Hussein. Everybody understands this?
Yes.
Okay. Write it down, please.
Sir, I also read somewhere that for an echo you have to stand at a specific distance from the surface.
Yes, we are right. We are at a distance, this predetermined distance that I forgot to write. You just need to stand in front of plane walls, so echo can be heard accurately, like it goes for towards the wall and comes back through the same distance, right? That's the only
Okay.
thing you need to do. Yep. Okay. So then let's go forward. Check this question. So it says a boy stands 150, he claps and he hears the echo. He immediately claps again. He continues to do this for some time. And the student has stopwatch. She starts the stopwatch on the first clap and stops it on the 11th clap. The watch reads 10 seconds. Which value do her measurements give for speed of sound? Okay, do you guys understand this? Now, so they're standing like this is a wall. They're standing like here, and this distance is 150 meters, right? So every time he claps, he waits before the next clap, and the sound goes like this and comes back, and he hears and then claps again. Do you understand? So then okay, he continued this for some time. After a student, she start the stopwatch on the first clap. First clap would mean he's clapped and then and stops on the 11th clap. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So 11 claps. And the time it takes is this. So how much time does it, like how much time would she be taking for just one clap? What do you guys say? Between one and the next. You got divide 11 by, I guess, 10, right? 10 by 11. What you get as time?
So it's like a long decimal number, like it's recurring 0.909090.
9090. Okay, seconds. Then what you're going to do is, in echo, speed is given by 2 times the distance over time, right? So 2 times 150 divided by 0.9090. What you get? I think 330. I think so.
Yes, sir. Sir, I did like 11 times 2 times 150 over 10.
Yeah, that's fine as well. That's fine.
Sir, I have a question.
Yes. Go ahead.
Understood how exactly we got speed, but I didn't understand how we derived time.
How we got time? Okay. I said if 11 claps are made in 10 seconds, then one clap would be made in how many seconds, right? Cross multiply this. So what you get?
Okay, how do we master it's 11 cups?
How do we do what? How do we know that it was 11 clap?
Yeah.
It's written, it says she starts on the first clap, she ends at 11 clap. So there are 11 claps.
I didn't hear that part.
Sorry?
So I didn't read carefully.
Like she starts on the first clap, so after first clap, she's the time starts. So you get one clap, one time for the first one, time 2, then 3, 4, 5, like 6. Do you understand like this?
Yes.
Yeah, and then we basically what we're doing is we're finding how much time basically that every clap he makes, right? So he's done 11 claps. So every clap he makes, so that would mean every time he claps, that would be his. But there's a situation that I just realized just now. Okay, and the situation is that what you're saying, there should be 10 claps, time for 10 claps, not 11. That's what you're saying.
Yes, sir.
Yes, that could be a reason. I just realized that this is something that is very, very interesting. Okay. All right. So, yeah, what she's saying, I'll tell you why. Basically, this answer is not entirely correct. I'll tell you why. What she's saying is that basically the time that we've taken is for 11 claps, but that's between this. Like, for example, there were 11 claps made. So she's saying first clap and then second, third, fourth, fifth, sixth, seven, eight. Okay, I don't have space. I'll write to here. One, two, three, four, five,
Sir, can I say
six.
something?
Yes.
When you pick time for 1 clap 1 second, the answer comes B.
Yeah, that's what I'm gonna explain then. That your answer is correct. Our answer was wrong. Why? What is happening is that she starts the stopwatch here. So then the next time she takes time was like she counts one. So that's one, and then that's two, that's three, and that's four, that's five, and the sixth interval was this, seventh interval, and eighth and nine, and there were 10 intervals because she stops here. If she had stopped at 12, then obviously it would be 11, but 10. So which means there were 10 claps, 10 time for 10 claps, not 11 intervals, right? So it should be 1 second then, right? And then we can write 2 times the distance over time. So 2 times 150 divided by 1 is 300, not this. So it has to be C. Right, Zainab? That's what you're saying? She's right, because it says that she stops at 11 claps. She didn't wait for 12 to begin, so then we have to take 10 time intervals. Is it clear, everyone? Well, that was a tough cookie question, but that's good. Okay, now we're gonna go to the next one, and we're gonna learn how to use a cathode ray oscilloscope to measure the speed of sound. So what you're going to do is you're going to say that there are going to be 2 microphones and a CRO and a sound pulse generator. When the sound pulse is generated, the first microphone is going to detect it, and there will be a reading on the CRO. CRO is just like, if you go to the hospital, there is a machine that shows heart rate, just like this. That is also CRO. This is also CRO. So that means that as the sound travels a distance t, it's gonna be detected by the next one, and there will be a sound signal again. So from the CRO, we can measure this time, and we know the distance already between the microphones, and use that, okay, to find the speed of sound. So we can write it like this. We can say 2 microphones placed a distance apart are connected to CRO when a sound pulse is directed towards the microphones each displays the wave after a short while on the CRO, we find the time interval using CRO, and then use speed equals to distance d over time t to find the speed of sound. Okay, like that. Anyone has a question here? Please let me know if you do not understand this.
So can you read it again because I can't understand it completely.
Okay, two microphones placed a distance apart are connected to CRO. When the sound pulse is directed towards the microphones, what happened to this? Okay, microphones, each displays a wave after a short while on the CRO. We find the time interval using CRO. Use speed, distance over time to find the speed of sound. Is it clear?
Yes.
Okay, very good. Okay, now, so should we go forward then? Perfect, perfect.
Sir,
Yes,
the third point, the each sound pulse displays the wave.
yeah, the wave after short while on the each microphone, not sound pulse, okay? Each microphone displays the wave after a short while on the CRO, okay?
I didn't get that point.
Like this microphone would detect first and then display a wave, and then the next one will detect and
Oh, okay,
like,
okay.
like this. Okay, pretty cool. And then,
So can you please wait?
okay.
Done, sir.
Okay, so then we're gonna go towards human hearing range. Like from this questions will be many. So basically, human hearing range is between 20 hertz to 20,000 hertz. The other variation is they can write 20 hertz and then they can say okay 20 kilohertz, so they can write it like this as well. Beyond this we have ultrasound, and before this we have infrasound. Okay, like that. And then just remember that we can only hear from this. That's it. That's all we need to know. So then ultrasound is an important thing. Obviously ultrasound has many uses. One of the uses of ultrasound is like medical scanning. Okay, that is also sometimes called as prenatal scanning. And then you got ultrasound can be used for cleaning of sensitive ornaments, like we don't want things to get damaged by putting normal cloth or using something else that one might scratch them. And then we can also use it as a sonar system. Sonar is basically finding like fishes, depth of water, etc. Okay, that's basically when sound pulse is sent and goes back. Now for the medical scanning, I just want to tell you two things about it. Like pulse of ultrasound is sent into body, okay, and then different layers reflect the pulse, and time taken to reach back determines depth, okay, determines depth of whatever layer you're looking at, layer of fat, layer of maybe tissue, layer of muscle, whatever, okay, like that. And obviously, and then the last point in that would be intensity received back tells us about intensity received tells us about the type of layer, okay, like it could be tissue. Sometimes they're like absorbed more, sometimes they're absorbed less. So let me write it here. Oh, I forget this, sorry. Okay, I'm gonna put this here so that we can write it. Sometimes this they might ask you this question, so we don't want to. Okay, and I also missed it. All right, then for the other one, I just want to tell you this one, the sonar system. That's basically like, suppose there's a like different boundary, different depth of water, a different depth of water at different points in the sea, so or river. So ship can send sound waves, and they're reflected off, so we can find how much time it takes, and then we can find the depth using speed of sound, like this. All right, sensitive ornaments is just like we put sensitive ornaments in water. Let's suppose we want to clean a silver spoon, okay, very expensive one, and then like we can send ultrasound, and ultrasound just removes the dirt or particles from it. So that's how it is done. Is it clear, everyone? Any questions? So medical scanning, you have to send a pulse of ultrasound, and then they get reflected back, and then at different rates, and when they reflected back, we can know the depth of the layer that we're looking at, and obviously the amount that comes back, some is absorbed, some is like coming back. So the amount of the intensity of the wave that comes back tells us how much wave, what type of boundary it is. So some boundaries, some layers absorb more, some layers just reflect more. Is it clear, everyone?
Sir, what about the beds, the echolocation? Is it included?
No, that's not. That's not. Okay, bats, like they just they might come in echo, but I don't think so. I've never seen a question like that. Okay. These are
I have a
different.
question.
Yes, please.
Could you just go back to the page where you were showing how a sound wave looks like?
Yeah.
I remember them seeing a question in the past paper that they said that like there's this wave and its frequency is the same, but they increased the amplitude, or they decreased the amplitude. Then
Okay.
how would you describe it?
That would be a louder sound. We're gonna look at that. Okay, just in a bit.
No, they said like it was in rarefactions and compression. So then they were saying, okay, then what would the particles be like in the compression, and what would they be in the rarefaction at a higher amplitude?
Okay, so that then it would be something like this. The compressions will be like almost the same. Okay, they have a like, but the gaps, amplitude increases, frequency same remains, and you have to show this kind of wave.
It was an MCQ, sir. Yes, it was like from 2020, and they said that there's this wave and its frequency is the same, but its amplitude
Okay.
is increased,
So
and then
then,
there are options
yeah,
that what
then
happens in compression and
I
rarefaction.
think the compression will be like more particles in it, and then rarefaction less particles and more. But the difference in the distance between them would remain the same if this was the MCQ. I've never seen that kind of one.
Okay, sir, it was somewhere I think in March or May, June.
Hmm?
It was somewhere in March or May, June of 2022.
Okay, I will try to find it. You also try to find it. If it's there, you can send it to me, okay?
Okay, sir.
Alright. So then I'm gonna go towards where do we want to go? Wait. Yeah. So that's it done. Now it says a sound wave passes through the point, the air pressure at that point increases and decreases 300 times every second. What is the description? Okay, what type of wave that might be?
Longitudinal.
Longitudinal. And 300 times per second would mean frequency equals to 300 times per second. That means 300 hertz. Is it within human hearing range or outside that?
Yes, it was within.
Yes, very good. So that would be B. And then it says the diagram shows which character sound waves do the numbers on the diagram refer. Okay, yes, please.
B.
Are you guys sure it is B? Yes, it is B.
Not B.
It is B. Because you see, it's 20 hertz and then 20,000 hertz. Do you understand? It should be in hertz frequency, okay? Then obviously this is an ultrasound question, and the reflection one you guys can do it as homework, as I know you guys can do it. That is the one that I told you already. Again, homework that you guys can do it. Ultrasound question. Again, ultrasound question. You can do it this yourself. Just practice. Let me know. Are you talking about this one? Okay. So now I'm gonna do this question. It says on figure at the center of a compression mark C. So compression is here. So we're gonna mark C, and then it says let's mark C, and then it says at the rarefaction mark. So at the center rarefaction it would be R.
Sir,
Yes.
sir, can you please show the homework questions again?
Yes. Just 3 questions after MCQs one. This one, which is from I think February March 21. This one, which is 19. Oh, I didn't. This is also homework. Basically, this whole page. These are the very similar questions for ultrasound. Okay, and this one, and I'm going to do this. So it says rarefaction and draw double-headed arrow to represent distance of 9. So we have a wavelength of this. So it's talking about 2 times the wavelength. Do you guys agree? So one, it would start from like rarefaction, compression, rarefaction. So this would be 1 wavelength, and then this would be 2 wavelengths. So this will be 0.90. Do you guys understand this? So it could be like this. And then it says frequency is 750, calculate the speed. So we have to do V is equal to F lambda. Speed of sound they've given, no. Frequency is 750, lambda is like 0.45. Yes, Amal, you do not understand this? Okay.
No, sir, I understood.
Okay, 750 times 0.45, so it's going to be 338 meters per second. Okay, write the units, please. Now it says suggest a medium through which the sound is traveling. Can you please tell me that?
Air.
Air. And why do you think it is traveling through air? Because you are right. Because in water it's 1500, and in steel it's 5000. Do you guys understand this? So you just give the reasoning that's much smaller than that. Then says another type of wave consists of compression and rarefaction is ultrasound. State one similarity between sound and frequency and ultrasound. What is the similarity?
Longitudinal?
Yeah, both are longitudinal. Okay. Yes, very good. And what about state in which wave sound is different from ultrasound? What is the difference here?
Higher frequency.
It's not within the range of audibility.
Yes, so 750 hertz is within human hearing range, okay? Unlike ultrasound. So you have to comment like this, okay? And then now we're going to talk about the last thing today, that's loudness and pitch. Loudness basically is basically depends on amplitude. So how do we do this? So I'm gonna make two waves, okay? Suppose let's make two waves, and also copy this diagram, okay, neat. And also I would like to remove this, okay, pretty good. Okay, and let's copy this. We need this on the other side as well. Oh no, okay, good enough. So loudness depends on the amplitude. So let's suppose if a wave is shown like this, and then another wave is shown like this, although both waves have same frequency, as you can see, but this is quieter and this is louder. Why it is louder? Because it has higher amplitude. Okay, so loudness depends on how high the amplitude is going to be. Pitch basically depends on frequency. So if a wave looks like this, and then another wave looks like this, although they have the same amplitude,
Same.
yes.
Why did you write quicker in the first graph?
I write quieter. Okay.
Okay.
All right. Okay. And the next one is going to be a low frequency. Okay. And that's going to be high frequency. And obviously, high frequency means that it's going to have higher pitch. So higher pitch is like shriller sound, and lower pitch is like lower frequency is like graver sound. Do you guys understand?
So can you repeat?
Like, low frequency means that it's going to be a grave sound. Grave means thick sound. High frequency will be like thin or shrill sound. Do you understand? Shrill? That's going to be shrill.
Okay.
That's going to be graver. Okay, is it clear? Like, men have graver sound and women have shriller sound. You get it?
Yes, sir.
Okay. So then the next thing is, it says a siren is emitting sound. As it passes, the sound becomes louder, higher pitched. What is happening to the amplitude and frequency of this? When something is coming near to you, right? So obviously you will hear it more. So the amplitude is definitely increasing. And because it's higher pitch, so frequency is increasing. That's correct. Very good. Yay. I think that's all. All right. So if you guys have any questions from this, let me know. I'm just gonna create